When you take an antiviral for COVID, it works through molecular sabotage. The drug looks like one of the building blocks the virus uses to copy its own RNA. The virus's replication machinery grabs that lookalike, slots it into the copy, and it ruins the copy. Remdesivir works this way. So do the other antivirals. Coronaviruses do something almost no other RNA virus does. They proofread. There's an enzyme called exoribonuclease that runs along behind the copying machine. It scans the new RNA, it finds the bad nucleotide that the drug snuck in, and it cuts it out. The sabotage gets thrown away. That single proofreading function is the biggest reason that remdesivir works less effectively against SARS-CoV-2 than similar drugs work against viruses that don't proofread. For 6 years, antiviral chemists have known that the proofreader was the problem, and they have not been able to see it clearly enough to design around it. Earlier images of the enzyme were too blurry to map which atoms were doing the recognition work. But a team at Iowa State published 2 papers yesterday with images of this enzyme at 2.4 angstroms. That's a new record for this particular enzyme. At that scale, you can see exactly which functional groups touch which, exactly where the modified nucleotides sit, and exactly the shape the enzyme is recognizing as flawed. 2 design pathways open from there. 1, redesign the antiviral so that the bad RNA it generates carries a shape that the proofreader doesn't recognize, so the proofreader simply walks past it and the sabotage stays in. Or 2, design a separate drug that binds the proofreader itself, locks it shut, and increases its grip on the modified RNA so that it grabs the bad material and refuses to release it. Either path needed the geometry that Yang's team just produced.